But there's another way that we can test this out. So instead of having these things hit and stick together, I'm going to use the spring on here to have these objects spring off of each other. So if you look underneath there, you can see that right in there, there is a spring. So when this object hits, it's going to partially compress that spring, and then that spring is going to push back and cause them to bounce off of each other somewhat. Okay. So let's see what happens in this case. So again, I'm going to throw these cards at each other. They're going to bounce off of each other instead of sticking together this time. And let's see what happens in this particular case. So again, I'm going to throw these two objects at each other, and let's see what we get. So I think we lost tracking. The tracking was not quite even on both of them, not quite lined up at the same time, because notice this one seems to hit a little bit before this one. All of the other cases, the timings were matched up, so I'm going to try this one again. So let's, again, we have some evidence of noise in the data that these times weren't quite matched up, but let's give this another try. So, and 3, 2, 1. There, that one seems to match up much better. So let's zoom in on this data. Okay. And let's look at what's happening. So before the collision, how would we measure these momentas? Well, we still have our 0.547. We didn't change anything with the masses. All that we changed was we were using this spring to launch the objects off of each other instead of using the Velcro to make them stick together or the magnets to have them spring off of each other. In our textbook model for momentum, oh, sorry, I moved off that point. Let's go right there. In our textbook model of momentum, the total initial momentum is negative 0.099 kilograms meters per second. But again, in this alternative model, we can't have negative momenta. So we'd have to add these up as positive values. So we'd add 0.169 plus 0.268. And I got 0.437 for that. After the collision. So after the collision, if we look at the standard textbook model of this, our total momentum ends up being negative 0.094. Again, in good agreement with our initial momentum, even though we have different ways of having these things run into each other, in all of these cases, momentum is conserved when there are only internal forces acting on that system, only forces between those two objects. And it can be any kind of force. We've used magnets to have these objects bounce off of each other. We've used Velcro to have these objects hit and stick together. That's still just an internal force between objects inside of this system. Now we're using this spring. There might be some friction on the spring, but that would still be, even if there were friction on the spring, that would still be internal to our system. So momentum would still be conserved no matter what interaction force is acting between these two objects, as long as there are only forces just acting between these two objects. I'm not pushing on another one. The track is level, so we don't have gravity, a part of gravity acting on one and not the other. Momentum is conserved in the Newtonian classic physics model. Momentum is conserved whenever there are only internal forces acting on the system. But going back to the alternative model, what would the momentum be after this collision? Well, there's no negative momenta, so we'd have to add up positive 0.199 plus positive 0.105, and I get 0.304 when I do that. Once again, in this alternative model, whenever we have any object going in the negative direction, this alternative model fails to accurately describe what's happening to this system. This claim that momentum does not care about direction that doesn't hold up when we're doing actual experiments. Okay. But there's another thing that we can note about this, because during that collision, for part of that collision, this spring was compressed. And we were lucky enough to get good tracking throughout that entire collision when that spring was partially compressed and when that spring was now letting go. But during that entire motion, notice that at every single point in there, the total momentum was staying the same. That black line for total momentum was staying the same. Even when the spring was compressed, when we were looking at the momentas of the two carts, their total momentum was staying the same. Momentum is not being stored in this spring. If the spring was storing momentum, we would expect that when the spring is partway through its compression during this collision, we would expect to see a change in that momentum, and then, well, that momentum would be returned back to the system when the spring went back to its relaxed state. But that's not what we see. Springs do not store momentum in the way that this alternative model predicts. Let's do one more case of this just to verify. I'm going to just push one cart at the other, and we're going to see how, again, that total momentum, even during the collision, even when this spring is being partially compressed, that total momentum is still staying the same. So let's do one more example of this. Here we go. Okay. So if we zoom in on that, and let's specifically zoom in on this part here. Okay. Again, during that collision, when the system is partially compressed, we're not getting this drop in momentum because the spring does not store momentum. However, if we were to look at the kinetic energy of the system, so let's highlight that exact same section. Zoom in on that, and look at what's happening to the energy of the system. So let me set this to 0, that part to 0, and let's set this part to, let's say, 0.1. Okay. This is a measure of how much kinetic energy the system is storing. Okay. The system has. So before the collision, we've got some kinetic energy. After the collision, we still have most of the kinetic energy. Again, there's a little bit of friction on that spring that's going to remove some of the energy from the system. But during that collision, we get this significant drop in the total kinetic energy of the carts. When that spring is compressed, it's not storing momentum, it is storing energy. So again, this alternative model makes the claim that springs store momentum. This data shows that they don't. It's not momentum being stored, it's energy being stored. When the spring compresses, some of that kinetic energy is being converted to spring potential energy, and when the spring launches those objects again, it gives, again, most of that energy back to the system. So overall, what does this tell us about how we can compare models? First, if I want to compare these models to figure out which one is viable, I need to find conditions where these two models, or any two models, make different predictions for the outcome of an experiment. And then we have to actually do that experiment and see which of our models matches with the data. In this case, all of our cases, no matter what kinds of objects that we had running into each other, whether we used the magnets to have the objects interact, whether we had Velcro having the objects stick together, whether we had this spring as the force that's acting on the two objects, as long as the forces in this system are all internal and there's no external forces, momentum is conserved. Direction matters in this conservation of momentum. So if I've got an object moving in the positive direction, we're going to call that a positive momentum. If I've got an object moving in the negative direction, we're going to call that a negative momentum. All of those predictions matched with the data to a high level of accuracy. Like, again, we were never more than a few % off of keeping all of that momentum just before and just after the collision. On the other hand, considering this alternative model, when everything was going in the same direction and we didn't have to worry about that objects going in the negative direction, it did match up. But as soon as an object was moving in the opposite direction, this model of momentum failed. It did not give conservation of momentum like the proponents of this model seem to think it should. We also found that if we use a spring for this collision, during the collision itself, the total momentum is staying the same. The spring does not store momentum. What it does store is kinetic energy. So, again, I hope this is a clear way of delineating between testing the predictions of two competing models and using the data to determine which of those models is actually viable. And I hope I've demonstrated that this alternative model is not viable. The classical physics, Isaac Newton's model of momentum, the kind that is taught in every reputable physics class, that one is supported by the data. All of this data that we've took supports that model. So that's it for this session. Again, I hope this was interesting. If you have questions, please throw those into the comments. I'm sure I'm going to get some comments back about this one. But again, be respectful when you're talking or responding, when you're posting or responding to any comments. And I'll see you in the next video.